Hi, networks and model uncertainties. Our team members are Abdul Chandra, Anav Nitin Kapadnis, Kola Anantraj, Omkar Modi, Shaman Pal, and Rohit Sutridhar. The two major schools of thought in probability theory are the Bayesian paradigm and the commonly used frequentist paradigm. In the frequentist paradigm, weights and data are considered as sets of outcomes. On the other hand, the Bayesian interpretation considers weights to be a hypothesis over some prior belief, and the data is used to update one's belief over weights. The probability distribution P of D given weights is the likelihood that encodes the aleatoric uncertainty in the model, i.e., the uncertainty that occurs due to noise in the data. Pw is the prior and Pd is the evidence. P of W given D is called the posterior that encodes the epistemic uncertainty or the model uncertainty that occurs due to the lack of knowledge of the model of the data generating distribution. This makes it obvious why standard neural network models lack and thus brings the need to build better Bayesian neural network and approximate inference algorithms. Uncertainty estimates help reduce overfitting and also helps reduce models' predictive distribution variance on unseen out of distribution data. Approximate inference is done either by sampling techniques or by using variational inference. The Bayes by backpropagation algorithm. This is one of the first reliably working learning algorithms for variational inference based Bayesian inference methods. Although variational inference is a good mathematical tool for Bayesian inference, it needs to be adapted for application in deep learning. The main problem being the stochasticity prevents backpropagation from functioning at the internal nodes of the network. Thus, new algorithms like Bayes by backprop had to be developed, which is actually a practical implementation of stochastic variational inference combined with a parametrization trick to ensure that backpropagation works as usual. In Bayes by backprop, we take a sample of elbow and perform backprop as usual. Although the process is very noisy, over a large number of samples, this should average out and converge to the maximized elbow, which is the objective of any Bayesian inference algorithm.
Now we will discuss the reparameterization trick. Usually epsilon is sampled, making it costly. So in this trick, we sample some function of epsilon that directly influences the log likelihood. This helps in translating uncertainty about the global parameters into local noise that is independent across data points. For example, in fully Gaussian parameterization weight, the weights are sampled according to the equation given in this slide. As to keep the variance inversely proportional to the mini batch size and to set covariance to 0, we need to sample W for each example in mini batch. So using reparameterization trick, the sampling is done directly from implied Gaussian distribution, making it efficient.
2015, Gairavani in the seminal paper discussed the concept of Monte Carlo dropout. Dropout techniques are used to reduce overfitting by deactivating a few random weights in a layer during forward propagation. In a normal neural network, dropout is not used during evaluation so as to utilize all the neurons in the model. But in Bayesian approximation, dropout remains active during evaluation as well. As a result, the outputs are different due to different neurons being used. The mean of the outputs treated as the actual prediction and the variance is used as the uncertainty of prediction or the model uncertainty called epistemic uncertainty.
Bayesian learning via stochastic gradient Langevin dynamics. So this method combines Robbins-Monroe type algorithms which stochastically optimize a likelihood with Langevin dynamics, which inject noise into the parameter update so that the trajectory of the parameters will converge to the full posterior distribution rather than just the maximum a posteriori method. So the Bayesian approaches typically use Monte Carlo techniques, which capture this uncertainty via the MCMC, that is the Markov chain Monte Carlo techniques. In this method, we will just consider a class of MCMC techniques called the Langevin dynamics, which take gradient steps, but also inject a significant amount of Gaussian noise into the parameter updates so that they do not collapse to just the MAP solution. So here we can see the parameter update step and the noise injection. So in the posterior sampling step, we consider the use of Langevin dynamics, and we derive an estimate of when the algorithm will transition from stochastic optimization to Langevin dynamics. Then the algorithm scales with the data size n and give a rough estimate of the number of iterations required for the algorithm to traverse the whole posterior. Finally, the obtained samples can be used to form Monte Carlo estimates of posterior expectations. Then we see the transition into the Langevin dynamics. The stochastic optimization smoothly transitions into the posterior sampling without changing the update equation. The method also allows for preconditioning, which can lead to significant speedups. Measuring the sampling threshold will only be important if one needs to represent the posterior distribution with a finite collection of steps.
Efficient SGLD for deep neural networks. Deep neural networks are becoming increasingly common in most applications. However, training them is very difficult, particularly because their loss function is highly non-convex and has lots of saddle points. Adaptive preconditioners allow the step size in stochastic gradient algorithms to conform to the local geometry of the parameter space over which learning takes place. Given the bad loss curvature of deep neural networks, this method particularly allows the step size to automatically take into account this local geometry, thus prevents getting stuck in saddle points and local suboptimal points. Preconditioned SGDs in general work very well, but may be inefficient in training expressive datasets. The preconditioned SGLD takes the efficient approaches of SGLDs and combines them with adaptive preconditionings to allow scaling the algorithms to larger datasets. These two equations govern the working of the algorithm, where G bar is nothing but the sample mean of the gradient using a particular mini batch. Of different Bayesian inference techniques on both classification and regression tasks. For classification, we use the standard MNIST dataset, and for regression, we generate a toy dataset using a Gaussian process of zero mean and k is the kernel, which here is the gradient basis function with diagonal Gaussian noise. Uncertainty caused by noise in the data, or the aleatoric uncertainty, can be quantified as the expected entropy of model predictions. Model uncertainty, or the epistemic uncertainty, can be measured as the difference between the total entropy and the allotropic entropy. Here the first one shows results for the toy dataset on varying mean and fixed variance data, and the second result shows varying mean and varying variance data. Second one clearly has more uncertainty estimates, as with change in variance the out of distribution data changes a lot, hence uncertainty in the model increases as well. Here we see how classification model of the MNIST dataset performs on out of distribution data. We created out of distribution data by simply rotating the images in varying angles. As we see that the model uncertainty increases up as the degree of variation from the original digit increases. Finally, to summarize our work, we studied different uncertainty estimation methods. Here we focused on Bayesian inference-based approaches. Knowledge of model uncertainty is very important for safety critical applications like robotics, finance, and medical data analysis. Out of the methods that we dwell deeper in in approximate Bayesian inference. Most of them are groundbreaking approximate inference algorithms that have been developed in the last 10 years, including sampling-based methods and variational inference-based methods. Finally, we saw how the application of these methods have been made into very recent examples for uncertainty-guided exploration in RL and uncertainty-guided steering wheel control. Thank you.